All right, so it's 10 o'clock, so we will get started. There we go. So this morning, what I've done is I've looked at your test scores and I dropped your lowest test. So your grade in class on Blackboard is with your lowest test grade dropped. And like I said on Monday, as we do more tests, I will update that every time we have a new test. So if you do worse on test 3 than you did on either test 1 or 2, then I'll just modify it so test 3 is now the test that's dropped. And so your grade will continuously reflect your current score. I've also opened up test 2 so you can see. That reminds me, I opened it up, but you probably can't see what you got right and wrong. So I'll fix that after class. I forgot to turn on that setting. So after class, that's what I'll do. But you should be able to then see, your answers, what you got wrong, and you should see what the correct answer was. I still am planning on making a very short video going over just a couple of the problems, some of the math problems, and some of the little more complex problems that gave people trouble. So that's where we are on that. On Monday, getting back to where we are currently, we were talking about energy, and we ended on this slide where we talked about heat and work, Q and W, and how they are not state functions, but you add them together to get a change of energy. And that's what this equation down here is saying. The change in energy, remember, delta means change when you see it in a mathematical equation. The change of energy is equal to heat plus work. So we're just going to begin with a little bit of review on this in the form of questions that we didn't get to on Monday. So let's jump right into it then. So question 3, I have 3 scenarios, A, B, and C. I want you to tell me in each scenario, are we doing heat? Are we doing work? Is there the energy exchange due to heat or is it due to work? And tell me if the sign of delta E is positive or negative in each situation. And yeah, I have a poll for this, so I'm going to put that up. So review what heat and work means, review what positive energy and negative energy means. And if you have questions, let me know. Otherwise, I will come back in a minute or two once people have time to think about this and answer it in the poll. All right, so hopefully you have had time to think about this, as it's been just about 3 minutes. So let's take a look at this. It looks like we're still more or less kind of confused on exactly what heat work means and what positive and negative energy means, as the answer seems to be kind of spread out everywhere. So yeah, let's look in this in a little detail then. So A, we have billiard ball number 1, and then it's moving, and it hits billiard ball number 2, causes billiard ball number 2 to go forward, and billiard ball number 1 works. So first off, you have to decide if this was heat or this was work, right? So our definitions is heat is energy exchange due to temperature differences. And work is force over a distance. So the billiard balls aren't at different temperatures, so we're not exchanging energy through thermal means. Billiard ball number 1 had a force, and it was moving across a distance, and then it hit that the second billiard ball. So this is definitely an example of work. And if the first billiard balls are system, the sign of energy was negative because it gave that energy to billiard ball number 2, which caused number 2 to move. So billiard ball number 1 was doing work, and it lost energy. Now, there is a little bit of heat energy due to friction. That is correct. Just a little bit, though. The majority of this work, or the majority of energy exchange, was due to work. B, we have a book, very high. It falls, hits the ground. So again, we're not exchanging energy due to temperature differences. We're having a force times the distance, or over a distance. So again, for the book falling, this is also an example of work. And up here, we have high potential energy when we're holding up very high. When it falls to the floor, that potential goes to kinetic. And then when it hits the ground, we lose all that kinetic energy. So again, the amount of energy in our system, the change in energy from being up top to the floor is negative. We lost energy. And like in A, some of the energy exchange is due to friction. And so some of it is due to heat, but only a little bit part of it. Most of it's due to work. You move that force, hits a distance, and you hit something else, and all that energy is transferred. And C, well, this is also work. Again, we're not dealing with temperature differences here. And if the father is pushing the daughter on a swing, and the daughter and the swing are the system, they're gaining energy, right? This daughter and swing are having work done on it by the surroundings, and the surroundings happen to be the father here. So those are some actual examples of, in this case, work, and ways we can start thinking of losing energy or gaining energy. So any questions about question 3 here? Can you go over the answers to the questions you have in the other PowerPoint? So sweat evaporating. Sure, I can do sweat evaporating. And I guess my system here is sweat. I actually don't know what I said is my system and my surroundings, so I'm just going to say sweat's my system. Okay. So this is heat because the way sweat works is that it's cold, and the body is hot. And so energy is transferred from the body to the sweat. That's how you cool down. And since the sweat is absorbing the energy from the body, let's say positive change in energy. A balloon expanding. Yep, the balloon is the system. All right, so this is work. This is pressure volume work. And we're going to see today work equals negative P delta V. Right? And so if a balloon is expanding, then it's pushing against the environment. And when it's pushing against something, it's doing work. If you are doing work, you are losing energy. So energy there should be negative because I'm physically pushing against my boundaries. So I'm losing energy doing that. I don't know. Aqueous chemical reaction, warm with external flame mixture. So if I have a chemical reaction and I'm warming it with fire, that's an example of heat because it's energy due to a temperature difference and fire is going in. So delta E is positive because the energy is going into it. Yep. So, and like I said on Monday, these things change if we decide to define our system somewhere else. Like if I decided to say, well, my fire is my system, well, we're still doing heat work, but you would have a negative change in energy there. Because remember, the energy of the system and the surroundings are the same value, but opposite signs. If something gains energy, then something else must lose that energy. So here are some actual calculations with it. And this will test your understanding of positive and negative again. So I have a system that absorbs 196 kilojoules of heat, not or heat, of heat. And the surroundings do 117 kilojoules of work on the system. Therefore, what is delta E? So the hard part here is to figure out the signs of Q and W. So I'll give people like a minute or so, and let me get up my little question timer here to see where you're at with this. But yeah, try and do this calculation and see if you can get the sign of heat and work correct. All right. So it looks like we have a majority of people done here. And most of you have got an answer, but not quite sure. So let's take a look. I have a system. Here's my system. And then everything else is my surroundings. So I absorb 196 kilojoules of heat. So if I'm absorbing it, it's going in. So that's a plus. And the surroundings do 117 kilojoules of work on the system. So this is probably the thing that's most confusing to you. When work is done on the system, I kind of think of that as like work is going into the system. So again, that's positive. If the system is doing work, then the system's losing that energy and it would be negative. But if it's done on the system, it's positive. So both of these values are positive. So Q is 196 plus 117. The change in internal energy is a positive 313 kilojoules. Questions about this idea? All right. And one more. So just to test your understanding of this idea again. So I have an air and inflated balloon, warms over a toaster for some reason, and absorbs 115 joules of heat. And as it expands, it does 77 kilojoules of work. Therefore, what's delta E? So since we just did this on 4, I'll just give you like a minute. Again, your main task is to decide what's positive and what's negative. So take a minute or so, figure out your signs, and I will be back to solve it. All right. As always, I find it helpful to draw pictures. Even though I can't draw, it's still a fun thing to do. I drew my balloon upside down. That's fine. That's a weird looking balloon. So there's my balloon. Here's my toaster. Toaster. And we have heat going into the balloon. So since it's going in, that's a positive 115 joules. Hopefully you paid attention to the units. It's expanding. So it does 77 kilojoules of work. So that's negative because it's doing work. So delta E equals Q plus W. So 115 joules minus 77,000 joules. Okay, so remember, kilojoules is different than a joule. There are 1,000 joules for every 1 kilojoule. So make sure your units are the same. When doing addition and subtraction, you cannot add things of different units. They have to be the same units. So that's probably the trickiest part of this one, to make sure you're watching your units And so the answer here is negative 76,885 joules of energy. All right. Questions about this or anything up to this point? All right. If not, or if you're still typing, continue to type. But I'm going to switch PowerPoints and go to the PowerPoint that I had prepared for today. Only one more week until April. So if there's any work being done, we subtract them. So the wording is, if the system is doing work, that means it's expanding energy. So like if you're like doing work by like picking up a boulder, you're going to expend energy to do that. But if work is being done on you, I guess the boulder example doesn't work for humans, but like if you're the person on the swing and someone is pushing you on a swing, work is being done to you, so you gain energy. That's a positive value. But if you're the person doing the pushing, well, you're doing work then because you're pushing someone. So work is negative because you're losing energy. That's how the wording goes. Is it being done on you or are you doing? Right. So let's move now on to talking about heat and heat capacity. And heat capacity is the amount of energy it takes to raise a temperature by 1 degree Celsius. And heat capacity depends on mass, because when we're talking about raising something by 1 degree, it takes a lot more energy to raise the temperature of the ocean by 1 degree than it does the water in your bathtub. So that's why we're saying it's dependent on amount. The more it is, the more energy you need. It's also dependent on material. So things heat up easier than others. So asphalt heats up really easily. You'll know this since you all live in Texas. You know this in the summer. You better not walk on pavement barefoot unless you want to burn foot. But grass is perfectly fine to walk on barefoot, even when it's 110 out, because it's harder to heat up grass than it is pavement. Same thing with cookware. The reason why certain cookware is chosen is because they will have low heat capacities. It's easy to heat up, like iron and aluminum cookware. It doesn't take that much energy. So that's why they're chosen. And something like stone, it's still used, but it just doesn't have, it has different heat capacities, and therefore it has different properties, different applications. But yeah, so that's what heat capacity is. How much energy it takes to raise the temperature of something by 1 degree Celsius depends on the material, depends on how much you have of it. So let's go to this idea of heat capacity to specific heat capacity. And specific heat capacity is giving a number to what I just said, right? So if I think the easiest way to understand specific heat capacity is look at the units. And let's look at lead. Lead has a specific heat capacity of 0.128 joules per gram centigrade. That's a point, not a negative. What that says is that it takes 0.128 joules of energy to increase 1 gram of lead by 1 degree or 1 degree centigrade. So that's what a specific heat capacity is. It's taking this general notion of a heat capacity and making it a more concrete number. How much energy it takes to raise 1 gram of substance by 1 degree centigrade. We're going to be using water a lot in this class for this, so that number is 4.18. I'm not asking you to memorize that or anything. Just have a star here as a just like pointed it out, and also looking at how how high the heat capacity of water is. So water is a great heat sink. If you live near water, you stay warmer longer during the winter because that water holds in a lot of heat. It also takes a long time to heat up water as well compared to like a lead or a gold. So water has an extremely high heat capacity. It takes 4.18, actually 4.184 joules of energy to raise 1 gram of water by 1 degree centigrade. And along with specific heat capacity, we have another term that's like it. It's molar heat capacity. And the only difference here are the units. Here is joules per mole centigrade. It's how much energy it takes to raise 1 mole of substance by 1 degree centigrade. That's the only difference, but it's still the same idea. How much energy to raise an amount of stuff by 1 degree centigrade. And to really do calculations with this is our equation. Q equals mc delta T. Remember, Q is heat, so that's our heat in joules. And that's equal to the mass in grams multiply by your specific heat capacity multiplied by your temperature change in Celsius. Right? So let's look at how the units work out here. Remember, we talked about this, I believe on Monday, that the SI unit of energy is the joule. So that's what our heat's going to be in. Mass, the SI unit of mass is the gram, multiplied by CS. That S means specific heat, and that's joules per gram centigrade. So multiplied by joules, divided by grams centigrade, multiplied by change in temperature, which is in centigrade. Grams on the top, gram on the bottom, they cancel out. Centigrade at the top, centigrade on the bottom, that cancels out. We have joules on both sides of the equation. So that's how we know our math works out. And so with this equation, we can do a lot of predictive stuff. If you give me heat, specific heat capacity and temperature change, I can tell you how much mass of a substance you had. Or if you give me mass, specific heat capacity, change in temperature, I can tell you how much heat you need to have that change in temperature. So a lot of cool things you can do with this equation. And we're going to get hands-on experience using this equation because this is chemistry. We love equations. So that gets us to our first question. You have 250 milliliters of water. This is at 37 degrees centigrade. You lose 342 joules of energy. What is the change in temperature? What is delta T then? And the density of water is 1 grams per milliliter. Specific heat capacity of water is here on the right. Our equation is here down here. So see if you can start taking this word problem, assigning your variables, and see if we can get an answer. For this, I'm going to put up our question timer again. If you have questions along the way, get stuck, let me know. Otherwise, try to muddle your way through it. And I will be back to work through it in a few minutes here. one thing I did forget, delta T. Remember, delta T always means temp final minus temp initial. That's what delta T means. What is a centigrade? Is it not Celsius? Celsius and centigrade are basically the same thing. Yeah. As well, it's not basically the same thing. They are the same thing. Centigrade is basically a way to say it's on a scale of 100, which Celsius is. Yeah. Two words for the same thing. No idea how to begin. What's your mass of water? What is the sign of heat? What's your specific heat constant? That's what you should be doing to begin with, right? You have in your equation there, Q equals mcs delta T, you have 4 variables. And anytime you only have one equation, you should only have one unknown variable. So you should always start with finding out what your unknown variable is. And it's given in the actual question. It's saying, what is change in temperature? So your unknown is delta T. So you should start with figuring out what Q, M, and CS are. And I will say, these type of questions, this will be on your test 3, this type of question, 100%. And so I will try to find more examples of this. And this question, every single year, a large percentage of the students get it wrong, and it's worth a lot of points because it's rather involved. So let's make sure we spend adequate time and practice getting this stuff right, because you will be seeing it on test 3, 100% guaranteed. You need, I think I need to convert 250 milliliters, but I'm not sure how to set up the conversion. This is something we talked about in our first month. So I want to convert from milliliters to grams. That's a density, right? Density says for every 1 gram of water, I have 1 milliliter of water. So let's set up our train tracks, 250 milliliters. For every 1 milliliter I have, that's 1 gram. So for water, it's easy. Since it's 1-to-1, 250 milliliters is 250 grams. Other liquids, other densities aren't 1-to-1, like 1 gram per 1 milliliter, but water is. So it's a simple calculation for us. Yep. All right. So that's 5 minutes. So let's take a look at this. All right, like I said, we want to start defining our variables. So Q, heat. I lose 342 joules of energy, right? So that's going to be my heat. We're doing heat work here. because we're talking about change in temperatures. So if I'm losing heat, that means it's leaving me. So it's negative 342 joules. That's my Q. My mass, we just did up here. If you're given a volume, you need a density to convert to weight. And that's going to be 250 grams. And our specific heat is 4.18 for water. And we're trying to solve delta T. You actually don't need this because I'm asking for change in temperature. If I asked you, instead of what is the change in temperature, what is the final temperature, then you would need the 37. As I said here, delta T equals T final minus T initial. And so you would plug your 37 in for the initial and try to solve final. But I'm not asking for that. I'm just simply saying, what is delta T? Right, let's set this up. Minus 342 equals, so let's do 250 times 4.18 or 4.18. And that is 1,045. And this will currently have units of joules divided by centigrade or Celsius because the grams canceled out, multiplied by delta T. All right, solve for delta T. Divide each side by 1045. This is in joules. So when you do that, it's negative 0.327 Celsius equals delta T. So we lost, or our final temperature, if I was asking for a final temperature, it would just be 37 minus 0.327, which would be 36.67 or 36.7. So that's our final temperature. But this question was only asking for delta T. So that is delta T. The change in temperature is negative 0.327 centigrade or Celsius. All right. Now that you saw that worked out, where did people get confused on? Where do you still have questions? Where did I lose you at? Any questions whatsoever? Yeah, so it's just like in real life, right? You get extra information. You just have to figure out what information you need. Good training. Just because I give you something does not necessarily mean you have to use it, which is always fun when I put that kind of stuff on a test to see how interesting ways people want to use extra information. That is definitely critical thinking. Do I actually need to use everything I'm given? So we always assume that whatever in units of J is the heat. If we are talking about a change in temperature, that is heat work. But there are other problems that deal with changes in energy due to work. I need to stop saying heat work. So if we're talking about change in temperature, that is energy exchange through heat. That's the only time you can assume, okay, joules is heat. If the question is talking about expansion or doing work or work done on it, then energy exchange is not heat in that case. So I can't say blanket yes. If you see joules, then that's heat. You kind of have to understand what's going on in the problem and how it relates to heat and work. That's why we did those series of problems at the very beginning today, where I just gave you examples. And your whole goal was to figure out, is this heat or is that work? So you have to take those skills and apply it to questions like this to understand, is this heat or work? See, everything ties together. You love this class. You are a special one. Every time professors, by the way, if you didn't know this, when you talk about other professors in front of like your current professors, like when you talk about me in like your Gen Chem class, they come and tell me what you say. I know, shocking, right? And most people hate this class. So I'm glad at least a few people enjoy it. All right. So we should have one more time, or time for one more question then. Yeah, the most common complaint I get is Dr. Andrews' tests are so hard. But I tell you what's on the test. We do the tests in class together. All right. So the last thing we're talking about here is exchange of energy. So let's say I have a piece of metal and I drop it in water. And I want to know if the metal is like hot and the water is cool, what is the final temperature these two substances will be at? And this is just an application of what we did on the last problem, except we have to do it twice. So remember we talked about on Monday, if a system is losing heat, then the surrounding is gaining heat. Well, in this example that we have on the right here, if this metal is hot and the water is cold, the metal will lose heat and the water will gain heat. And the amount of heat loss and gain are the same value but opposite signs. And like I said, we talked about this on Monday. It's just an expansion of that idea. And that's what this means. Q metal equals negative Q water. The Q is the same numerical value, but just different signs. So in the way I'm writing it, the metal might lose 100 joules. Therefore, the water has to absorb those 100 joules. And since we're talking about energy exchange due to heat, we can calculate Q using specific heat capacities. So if Q metal equals Q water, we just talked about on the last slide how heat equals mass CS delta T. So I'm plugging that in for Q metal here, mass of metal, specific heat of metal, delta T of metal equals negative Q water. And again, same equation, but now I'm talking about mass of water, CS of water, delta T of water. And a common question I always get is, does it matter which side the negative sign's on? It does not. Q metal equals negative Q water is the same thing as negative Q metal equals Q water. So when doing heat exchanges between materials, it does not matter what side of the equation the negative sign's on. It's just important you remember to put one there. The math will always work out, no matter what side of the equation you put a negative on to begin with. Just make sure you do that. So that is how we can calculate thermal energy transfer using the calculation we did on our last problem. So here's a question you're likely to see on the test that is heat energy transfer. So since time is low, I'm going to actually start drawing our picture for us. So we have a silver block. And the heat capacity of a silver block is 0.235. So CS is 0.235. Initially, T initial is 58.5. I put this into 100 grams of H2O. So let me get a blue pen. So it's submerged in water now. water, and I'm going to use blue to talk about water. Water, the initial of water temperature is 24.8. The weight is 100. Specific heat capacity is 4.18. If the final temperature of the mixture is 26.2, okay, so the mixture is both the silver and the water. So T final of water is 26.2. T final of silver is 26.2. Given all that information, tell me how heavy that metal block had to be. So, like I said, for time's sake, I kind of already showed you how I would attack such a problem. Start by drawing, start by labeling out my, my variables. Here's our equation. Tell me what mass of metal is. So I'll give you like a minute or two, start plugging in, working this out. Remember, delta T is always final minus initial. And then I will be back to help you solve this. All right, time's running low, so let me start filling in this equation for us. M, I don't know. CS of metal, 0.235. Delta T of metal, final minus initial. So final is 26.2 minus the initial of 58.5 equals negative. Again, we just need a negative side on one side. Does not matter which side. Negative mass of water is 100 times the CS of water, 4.18, times delta T of water, final minus initial, 26.2 minus 24.8. And so what I did is I just calculated the water side first. And there's a lot of ways to go about solving this equation. So I first did all the calculations on the right, and I got Q of water is negative 585.76. That should be in joules. So that's 100 times 4.184 times this parenthesis. Then what I did is I divided this by delta T metal, which is 26.2 minus 58.5. And when you take Q water divided by delta T metal, I got 18.13498. Again, I'm going to save sig figs for last. Then you take this. So I did let me actually do this. So this is Q water divided by delta T metal. That's what I'm showing here. That sum, I'm taking that and dividing it by CS metal, which is 0.235. And the weight of metal is 77.17 grams. And this should have, I believe, I think only 2 sig figs, because this will only have 2 decimals. So sig figs wise, that should be 77 grams, because 26.2 minus 24.8 is 1.4. That's going to be our limiting sig fig. So I know I did this one a little bit quick compared to the other questions we did today. And this question, like I said, is going to be one of the ones that I predict that will give people the most trouble when it comes to the test. However, it's just one long algebra problem. And your job is just to figure out what's your one unknown and go on from there. Yeah, if you did it a different way, again, this is all multiplication and division. So you can do it a lot of different ways to get the same answer. As long as you follow the rules of math and make sure you follow your order of operations, you should come out with the same answer. Right. Any questions about this? I know we're running a little late here. Could we have done both sides at the same time, divide the left by the right? Yeah, you can multiply the left first and then divide that answer by what you got on the right. That's totally legit too. If you remember from your math class, the order in which you do multiplication and division can be in any order as long as you follow like order of operations, more or less. All right, so that's it for today. I will be putting up a homework like always to give you more hands-on practice with these problems. And I will scour the internet to see if I can't find specific heat example problems and make like a little worksheet out of that. As I said, this by far is the hardest problem on test 3. So I want to make sure you have plenty of opportunity to practice that. Otherwise, if you have questions, as always, let me know. Other than that, I have nothing for you. So have a good rest of your Wednesday. Take care.